The Prime Spiral Sieve radial geometry and Chordal algorithms demystify the prime number sequence. My general view of mathematics is that most of the complicated things we learn have their origins in very simple examples and phenomena. Dr. Richard Evan Schwartz, Chancellor's Professor of Mathematics, Brown University. Deep and satisfying mathematics can arise from simple beginnings. Vicky Neal, PhD, Additive Number Theory. Everything should be made as simple as possible, but not simpler. Albert Einstein. Simplicity is the ultimate sophistication. Leonardo da Vinci. Seek simplicity and distrust it. Alfred North Whitehead. Introduction. Prime numbers have been deemed mysterious for more than 3 millennia. Any claim to have demystified them, as the title of this work boldly declares, will justifiably be met with skepticism. Regardless, deciphering how primes distribute in literal mathematical terms deepens the mystery when you consider the profoundly beautiful algorithms and rotating symmetry groups that govern where on the number line these atoms of the number universe fall. We explore these patterns in great depth with a powerful analytical tool, a deterministic algorithm, and ever-expanding geometry in the form of a spiral sieve, the Prime Spiral Sieve. Its Archimedean orbits encompass 8 arithmetic progressions that double as multiplicative initiators of geometrically expanding period 24 factorization cycles. These deterministic sequences intertwine like an octal helix and ultimately determine the distribution of all prime numbers greater than 5, i.e., starting with 7. We will also demonstrate how the Prime Spiral Sieve can geometrically shapeshift into a rectangular matrix, 4-sided pyramid, or continuous triangular wave. Prime Spiral Sieve configurations, and we will show how the first 3 primes, 2, 3, and 5, although excluded from our factorization domain by definition, are nonetheless omnipresent in the form of structure serving to contain and direct the aforementioned factorization algorithms. One might call what follows primal math, in that its modular arithmetic is revealed to be deeply rooted in the most deceptively primitive mathematics of all digit sum and digital root arithmetic, and especially the Vedic square that originated in ancient India. This methodology, combining congruence relations with digital root cycles, exposes palindromes and complex polygons that illuminate our understanding of how prime numbers are formed. Apply period 24 model of primes and composites in a study of statistics and modular arithmetic of prime numbers. An abstract of the referenced study can be found at Notes on Prime Numbers, their numerical statistics and patterns. Why? Modular arithmetic and the eightfold period 24 model. The period 24 patterns in question, relating to modulo 90 factorization algorithms and the digital root dyad cycles generated by twin primes, are discussed at length on our page devoted to them, factorization and prime number sieving algorithms and geometries. The sequence populating the Prime Spiral Sieve, pictured below, can be variously defined as natural numbers co-prime to 30, i.e., not divisible by 2, 3, or 5, and given no prime number, 5 is divisible by 2, 3, or 5, it's axiomatic that our factorization domain contains all prime numbers. 5 starting with 7, the number 1 being silent, and their multiplicative multiples, beginning with 7 root 7 equals 49, the first composite number in the sequence. It follows that all members of our domain are relatively prime, aka coprime or mutually prime, to 2, 3, and 5. Natural numbers 1, 7, 11, 13, 17, 19, 23, 29 modulo 30, which parse into 8 arithmetic progressions, each with a common difference of 30 between consecutive terms. Group U, 30, x 1, 7, 11, 13, 17, 19, 23, 29 of positive integers smaller than and relatively prime to 30 with multiplication modulo 30. 1 plus 6 plus 4 plus 2 plus 4 plus 2 plus 4 plus 6 plus 2. Repeat, but 30n plus 1, 30n 7, 30n plus 11, 30n plus 13, 30n plus 17, 30n plus 19, 30n plus 23, 30n plus 29. Natural numbers modulo 30 that distribute to the following 8 angles. All odd numbers with digital root of 1, 2, 4, 5, 7, or 8, and final digit of 1, 3, 7, or 9, the first 8 of which are 1, 7, 11, 13, 17, 19, 23, 29. Note: throughout this site, you'll find references to various cumulative sum and indexing formulae. For convenience, we've created a page dedicated to them: cumulative sum and indexing formulae. It's important to emphasize that the beautiful symmetries encountered within this factorization domain, both numeric and geometric, are largely a consequence of patterns rooted in its period 24 digital root, which has the following repetition cycle: 1, 7, 2, 4, 8, 1, 5, 2, 4, 1, 5, 7, 2, 4, 8, 5, 7, 4, 8, 1, 5, 7, 2, 8, 2, repeat. This 24-beat cycle is equivalent to 3 rotations around the prime spiral sieve. The first 24 members of our domain and their digital roots, therefore, are especially important given they set the initial conditions for all that follows. To emphasize this period 8/mod 30 telescopic stretch to period 24/modulo 90, we occasionally group this sequence as n were 1, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 49, 53, 59, 61, 67, 71, 73, 77, 79, 83, 89, modulo 90. The modulo 90, period 24 digital root repetition cycle of our domain allows us to sieve and sequence by digital root, dr, as listed below, and documented by the author on the online Encyclopedia of Integer Sequences. Dr. 1 = n, 1, 19, 37, 73. Mod 90, 1 plus 18 plus 18, 36 plus 18. Repeat. oeis.org, A301617. Dr. 2 = n, 11, 29, 47, 83. Mod 90, 11 plus 18 plus 18 plus 36 plus 18. Repeat. oeis.org, A301621. Dr. 4 n, 13, 31, 49, 67. Mod 90, 13 plus 18 plus 18 plus 18 is 36. Repeat. oeis.org, A301622. Dr. 5 en, 23, 41, 59, 77. Mod 90, 23 plus 18 plus 18 plus 18 plus 36. Repeat. oeis.org, A301623. Dr. 7 en, 7, 43, 61, 79. Mod 90, 7 plus 36 plus 18 plus 18 plus 18. Repeat. oeis.org, A301628. Dr. 8 n, 17, 53, 71, 89. Mod 90, 17 plus 36 plus 18 plus 18 plus 15. Repeat. oeis.org, A295869. When the modulo 90 matrix listed above is color-coded to highlight its 12 lateral 90 sums, 12 is 90, x 1080, x 360, x 3, perfect symmetry is exposed. Prime number digital root congruence matrix. In our section devoted to twin primes, we demonstrate how to configure the above table to sieve and/or sequence twin prime candidates by digital root dyads. Note: the easiest and fastest way to determine modulo 90 congruence of a whole number is to reduce all digits antecedent to the number's terminating digit to their digital root. For example, the first 3 digits of 2497 reduce to digital root 6, leaving 67, which equates to 2497, 6067 shares or mod 90. Keep in mind that 9s count as 0 when calculating digital root. This is sometimes called casting out 9s. Below is a picture of the Prime Spiral Sieve showing rotations spanning numbers 1 through 259 of the infinite sequence populating the sieve, as defined above. Prime Number Spiral Sieve. Hidden deep within this sieve, a radical spin on modulo 30 wheel factorization, are mysteriously beautiful symmetries and geometries, profound in their implications. This sieve not only forms the basis of an extremely efficient and widely used prime number sieving algorithm of the non-probabilistic kind, which we provided links to above, but it demonstrates how prime numbers are distributed within a radial geometry that effectively defragments the Ulam spiral and ultimately leads us to the theory of everything. This domain, once fathomed, reveals itself to be a beautiful mathematical object. It can be conceived as both an infinite spiral and, when matrix factorized at the digital root level, an ever-expanding four-sided pyramid structured by palindromic sequences. Regardless, the real power of this geometry becomes evident when we triple it dimensionally and explore modulo 90 factorization symmetries at the digital root level, culminating in the magic mirror matrix, a calculatory geometry that serves as a prime factorization sequencer accounting for the first 1,000 prime numbers exactly, and ultimately all prime numbers. 5. Most profoundly, we'll discover how the 8 spiraling factorization algorithms, i.e., the multiplicative multiples of the domain's sequence starting with 72, that ultimately account for every composite number within the prime spiral Sieve's orbits, are structured by rotational symmetry groups in the shape of equilateral triangles. 1047, 8, 3, We'll demonstrate how these can be configured to form 3x3 matrices, which in turn extrapolate into beautiful complex polygons. Only elementary arithmetic and geometry are required to understand what you find on this site. This minimal requirement is reflected by Mazur and Stein in prime numbers and the Riemann hypothesis. It is striking how little you actually have to know in order to appreciate the revelations offered by numerical exploration. Foundations. Surprisingly, playing with arithmetic can lead us to unexpected and profound discoveries that point toward deeper mathematics and sometimes even deeper science. Pradeep Mutalik, Ph.D. The Puzzling Power of Simple Arithmetic. Quanta, April 20th, 2021. The genesis of most, if not all, repeating prime number patterns described in the mathematics literature, e.g., twin primes, Cullen primes, Chen primes, sexy primes, cousin primes, Sophie Germain primes, Siamese primes, Cunningham chains, the list goes on, can be readily deciphered using the Prime Spiral Sieve as an analytical tool employing modular arithmetic, and specifically, modulo 30 relationships. Here are 2 examples supporting this claim. IEEE, using this sieve to analyze and predict Siamese primes, N2 and N2 plus 2 are primes, and Sophie Germain primes, P and 2P plus 1 are primes, keeping in mind that these will make more sense after you've read what follows. The most obvious of these repeating prime patterns are the 3 twin prime distribution channels, described at length on this site. These and all other such repeating, albeit intermittent and seemingly random patterns, are fundamentally subpatterns of the set of natural numbers not divisible by 2, 3, or 5 when arrayed in 8 dimensions, whether in a matrix or spiral form. The illusion of randomness results from the overlapping sequences of the 8 algorithmic chord progressions that factorize the domain. We will be discussing these progressions when we get to prime factorization. The first rotation of the sieve, comprised of 8 members, 1, 7, 11, 13, 17, 19, 23, and 29, is the deterministic key to everything that follows. These are the first 8 counting numbers not divisible by 2, 3, or 5, a sequence which by definition includes, and only includes, 1 and all primes, so was 7, and their multiplicative multiples. And, as you'll see below, it's conjectured that the entire set can be generated by a simple expression involving 2, 3, and 5. The inference of this conjecture is that all prime numbers greater than 5, i.e., starting with 7, can be produced by this expression. Note: given our domain is limited to numbers 1077,011, 13, 17, 19, 23, 29, modulo 30, only phi m is 830, or 26.66% of natural numbers, n, x, 0, 1, 2, 3, need be sieved. For example, to illustrate the proportionality of this ratio, we find that 25% of the first 100 natural numbers are prime, while 72% of numbers not divisible by 2, 3, or 5 are prime. And curiously, if we count 2, 3, and 5 in after the fact, we get 75%, or exactly 3 at 25%. Also note that if you plug the number 30 into Euler's totient function, phi n, fi 38, with the 8 integers, known as totatives, smaller than and having no factors in common with 30 being 1, 7, 11, 13, 17, 19, 23, and 29, i.e., what are called prime roots above. 30 is the largest integer with this property. The integer 30, product of the first 3 prime numbers, 2, 3, and 5, and thus a primorial, plays a powerful role organizing the array's perfect symmetry, viz., in the case of the 8 prime roots, 1 plus 9 tons is 30, 7 plus 23 and 30, 11 plus 19 is 30, and 13 plus 17 and 30. In the Number Mysteries, well-known mathematician Marcus du Sautoy writes, "In the world of mathematics, the numbers 2, 3, and 5 are like hydrogen, helium, and lithium. That's what makes them the most important numbers in mathematics." Although 2, 3, and 5 are the only prime numbers not included in the domain under discussion, they are nonetheless integral to it. First of all, they sieve out roughly 73% of all natural numbers, leaving only those nominally necessary to construct a geometry within which prime numbers can be optimally arrayed. The remaining 26.66%, to be a bit more precise, constituting the array can be constructed with an elegantly simple interchangeable expression, or power series if you prefer, that incorporates the first 3 primes. It's conjectured that this manifold series ultimately consists of all and only the numbers not divisible by 2, 3, or 5 and their negatives, which includes all prime numbers 5, more below under the heading, Conjectures and Facts Relating to the Prime Spiral Sieve. What is critical to understand is that the invisible hand of 2, 3, and 5 and their factorial 30 create the structure within which the balance of the prime numbers, i.e., all those greater than 5, are arrayed algorithmically as we shall demonstrate. Primes 2, 3, and 5 play out in modulo 30, 60, 90 cycles, decomposing to 3069 sequencing at the digital root level. Once the role of 2, 3, and 5 is properly understood, all else falls beautifully into place. Deep symmetries. Physicists have exalted symmetry to the position of the central concept in their attempts to organize and explain an otherwise bewildering and complex universe. Mario Livio, The Equation That Couldn't Be Solved: How Mathematical Genius Discovered the Language of Symmetry. The Prime Spiral Sieve possesses remarkable structural and numeric symmetries. For starters, the intervals between the prime roots and every subsequent row or rotation of the sieve are perfectly balanced, with a period 8 different sequence of 6, 4, 2, 4, 2, 4, 6, 2 duos. The entire domain can thus be defined as 1 plus 6, 4 plus 2, so 4 plus 2, 4 plus 6 plus 2, repeat. Hasio. As we've already suggested, the number 30 figures large in our modulo 30 domain. The prime spiral sieve is Archimedean in that the separation distance between turns equals 30 ad infinitum. The first 2 rotations increment as follows: root prime symmetry involving 30s. Interestingly, the sum of the second rotation equals 360, the product of the first 3 primorials, 260, 130 equals 360. And when you multiply the first 5 Fibonacci numbers in sequence, you produce 1, 2, 6, and 30. And speaking of the Fibonacci number sequence, there is symmetry mirroring the above in the relationship between the terminating digits of Fibonacci numbers and their index numbers, equating to members of the array populating the prime spiral sieve. Fibonacci terminating digit symmetry. Remarkably, the sequence of Fibonacci terminating digits indexed to our domain, natural numbers not divisible by 2, 3, or 5, 13,937,179, see graphic above, is a prime number and a member of a twin prime pair with 13,137,177. In case you're wondering, 13,137,179 is not a reversible prime, as the reversal is a semi-prime. 9,161 271 equals 97,173,131. However, given all the repunits that follow, we take note that both of the reversal's factors are congruent to 11, mod 30 and 90. Note: repunits are abbreviated Rn, where n designates the number of unit ones. Thus 1 is R1 and 11 is R2. Perhaps most remarkable of all, 13,937,179 when added to its reversal, 97,173,931, equals 111,111,110. In strict digital root terms, the sum is 11,111,111, or R8, and the entire repeating and palindromic Fibo sequence end-to-end, equivalent to 2 rotations around the sieve, gives you this palindromic equivalency: 1,393, 117, 997,173,931, 11,111,111, mod 107, 111, 110 sen. And interestingly, 11 to 11, 111, 111, 111,111,110, 1, 2, 3, 4, 5, 6, 7, 6, 5, 4, 2, 1, 0. Another point of interest: the terminating digits of the first 8 Fibonacci numbers indexed to our domain, 139,37179, contain 2 each, 1s, 3s, 7s, and 9s. This is also true of the terminating digits of the first 8 members of our domain, 107,37939. Echoing the Fibonacci patterns just described, the terminating digits of the prime roots, 17,137,939, when added to their reversal, 93,973,171, equals 111,110. And note that 111,111 to 111. 111,111,110 in 1, 2, 3, 4, 5, 6, 7, 8, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yet another related dimension of symmetry: the terminating digits of the prime root angles, 24,264,868. See illustration of Prime Spiral Sieve, when added to their reversal, 86,846, 242, equals 111,110. Not to mention, this sequence possesses symmetries that dovetail perfectly with the prime root and Fibo sequences. And when you combine the terminating digit symmetries described above, capturing 3 rotations around the sieve in their actual sequences, you produce the ultimate combinatorial symmetry: terminating digit symmetries. Here's yet another fascinating dimension of symmetry: the pattern of 9s created by decomposing and summing either the digits of Fibonacci numbers indexed to the first 2 rotations of the spiral, a palindromic pattern, 13937179971173931, that repeats every 16 Fibo index numbers, or similarly, decomposing and summing the prime root angles. The decomposition works as follows. In digit sum arithmetic, this would be termed summing to the digital root. F17, the 17th Fibonacci number, equals 1597, equals 1 plus 5 plus 9 plus 7 equals 22, equals 2 plus 2 equals 4. Fibonacci and prime root angle. Terminating digit symmetries. Another dimension of symmetry involves the terminating digits of the prime roots and their angles, those paired with like terminating digits being separated by 120 degrees and 11 132 degrees, 13 156 degrees, and 23 276 degrees, 7 84 degrees, and 17 204 degrees. 19 228 degrees, and 29 348 degrees. Another consideration with regard to terminating digits is that one can easily construct, by combining all numbers with the same terminating digits, a four-fold arithmetic progression in increments of +10 and +20, starting with 1, 7, 13, and 19. Thus, combining 112 degrees and 11 132 degrees gives us 1, 11, 31, 41, 61, 71, 91, plus 10 plus 20, n. Combining 784 degrees and 17 204 degrees gives us 7, 17, 37, 47, 67, 77, 97, plus 10, 20, n. Combining 13 156 degrees and 23 276 degrees gives us 13, 23, 43, 53, 73, 83, 103 plus 10 plus 20, n. And combining 19 228 degrees and 29 348 degrees gives us 19, 29, 49, 59, 79, 89, 109 plus 10 plus 20, n. Looking at the array in this configuration, however, has borne no fruit. As fascinating as the symmetries examined above may be, they are but a prelude to the beautiful patterns we'll explore when we discuss digital root sequencing and the trinity of triangles and magic squares rooted in Vedic arithmetic that drive factorization algorithms within this domain. And finally, if you want to jump ahead and view the perfect palindromic symmetry found at the heart of factorization, check out the magic mirror matrix that maps factorizations at the digital root level and accounts for the first 1,000 prime numbers exactly. The Prime Spiral Sieve. Around the perimeter of the spiral sieve, pictured below, you'll note that the 8 radii are labeled in relation to their modulo 30 prime roots, i.e. 1, 12 degrees. 7, 84 degrees, 11, 132 degrees, 13, 156 degrees, 17, 204 degrees, 19, 228 degrees, 23, 276 degrees, and 29, 348 degrees. These relate to the fact that the circle is segmented into 30 equal sectors, or radii separated by 12 degrees. 30 to 12 degrees, 8 radials that are the focus of this study are shown. Prime Spiral Sieve. This sieve exposes the twin primes, aligning as they do along 3 distinct distribution channels. One obvious implication is that those numbers in the array congruent to 7 lambs modulo 30, radial angle 84 degrees, and 23 thous modulo 30, radial angle 276 degrees, can be excluded as twin prime candidates, and by definition, all prime numbers distributed along these 2 diagonals, with the exception of 7, which is twinned with 5, will be what are known as isolated primes. Later, we explain how twin prime candidates can be segregated from all other positive integers and be partitioned into 3 columnar sets covertly aligned by the first 3 prime numbers, encoded in angles. Conjectures and facts relating to the prime spiral sieve. The array is rooted in the first 3 prime numbers, 2, 3, and 5, and their product, 30, the third primorial. This array reveals that the first 3 primes play a very special role in creating the symmetrical geometries that align the distribution of all subsequent prime numbers, thus distinguishing them from all other primes. Primes 2, 3, and 5 are like 8-legged spiders assigned to spin the beautiful spiraling web in which the remaining prime numbers are arrayed along assigned threads. For a detailed listing of number 30's attributes, plus reference links, click here, the number 30. It is conjectured that all and only the numbers in this array and their negatives can be derived using the interchangeable expression incorporating the first 3 prime numbers, 2, 3, and 5, where x has 2, y has 3, and z 5. Thus, xn1 1 plus zn, xnzen plus yn, and nzen plus xn. For example, 2, 5, 33 equals 13, 32, 3, 2 equals 73. This expression, therefore, potentially generates all numbers not divisible by its 3 terms, 2, 3, and 5, including all prime numbers 5. Note: for any given number in the array, there are multiple and possibly an infinite number of solutions. For example, the number 11 can be expressed as xy plus equals 11, x2y2 z2 equals 11, z2y x6 equals 11, etc. More examples below. 2003 5 in combo equal n, not div 2, 3, or 5. All prime numbers, with the exception of 2, 3, and 5, are distributed along 8 diagonals in intervals of 30, starting with prime roots 1, 7, 11, 13, 17, 19, 23, and 29. Thus, 1, 31, 61, 91, n, 7, 37, 67, 97, n, etc. The products of any combination of factors in the array equals a number in the array, e.g., 7, 11, 13 equal 1001, etc. Conversely, all factors for composite numbers in the array can be found in the array. Every composite number in our modulo 30 domain can be derived from the product of two terms in the domain multiplied together. And these multipliers need not necessarily be prime themselves. For example, 5831, which is congruent to 11, modulo 30, and therefore in the array, is the product of 49, 119, equals 50831. In this example, neither 49, 7, nor 119, 17, are prime, though both are members of the array. The sum of any sequential odd number of addends in the array equals a number in the array, e.g. 1 plus 7 plus 11 equals 19, 1 plus 7 plus 11 plus 13 plus 17 equals 49, etc. Because the digital roots of all prime root angles are either 3 or 6, any prime root angle times another will produce a product whose digital root equals 9, e.g. PR7, 84 dij, x, PR29, 348 dij, equals 84 is 348 equals 29232 equals dur9. Any number in the array x30 plus 1 equals a number in the array. The sum of the angles for 2 to 24 dij, 336 dij, and 560 dij equal 120 dij, and the sum of the prime roots 1 plus 7 plus 11 plus 13 plus 17 plus 19 plus 23 plus 29 also equals 120. This is because the prime roots are an arithmetic anagram for the angles of the first three primes. Thus, 11 plus 13 equals 24, 17 plus 19 equals 36, and 1 plus 7 plus 23 plus 29 equals 60. The sum of the second rotation equals 360. 224 degrees, 336 degrees, 560 degrees equals 360 degrees. The array reveals beautifully symmetrical relationships, mod 30 of all numbers in this array, and thus all primes other than 2, 3, and 5 must be 1, 7, 11, 13, 17, 19, 23, or 29. The sum of the digital root sums of the prime roots 1, 7, 11, 13, 17, 19, 23, 29. A 1, 7 plus 2, 4, 4, plus 8 plus 1 plus 5 plus 2 equals 30. This sieve reveals why all primes 5 are adjacent to a multiple of 6, as the prime root radii are adjacent to 672 degrees, 12 on 144 degrees, 18 216 degree, 24 288 degree, and 30 was 360 degrees. And you'll note that the digital root sums of all adjacent angles equal 9. The modulo 90 congruence of any member of this domain can be determined by digital root and terminating digit configured in an XY matrix. Arrayed by digital root, 1, 2, 4, 5, 7, 8 dual on the vertical axis, and by terminating digits 1, 3, 7, 9 par on the horizontal axis. Take, for example, number 179, which happens to be prime. Its digital root equals 8 and its terminating digit equals 9. Looking at the table below, we can quickly determine that 179 is congruent to 89 modulo 90. By definition, prime factors for all composite numbers within this domain must originate from within it, which is why all composite numbers are reducible to one or more modulo 90 congruence dyads traceable to the first 24 members of this domain. Modulo 90 congruence determined by digital root and terminating digit factorization and sieving methods. Employing the Prime Spiral Sieve. For a detailed discussion of efficient factorization and prime number sieving algorithms, as well as an in-depth analysis of the 8-chord progression and deterministic modulo 90 digital root dyad sequences underlying all factorizations employing this sieve, click here. Factorization and prime number sieving algorithms. If you use Python, the computer programming language designed for the development of scientific, engineering, and mathematics applications, and want to cut to the chase, check out the MIT licensed Python module dubbed PyPrimes. It's designed to speed test non-probabilistic prime number sieving algorithms, i.e., deterministic sieves that precisely account for all prime numbers within a given range. These include the sieve of Eratosthenes, wheel factorization, and the Prime Spiral Sieve, referred to by its alternative name, Prime Spiral Sieve, or simply Prime Spiral. Here or here at code.google.com. The programmer, we're pleased to report, rates the Prime Spiral Sieve fastest best and recommends it as the preferred way of generating prime numbers, compared to the several sieves tested. Counting primes. The Prime Spiral Sieve can be used to calculate the number of prime numbers within a stated range, from 0 to n or PRX, using the standard notation, with absolute precision, albeit in several unconventional steps. It does so by employing the 4 elementary operations of arithmetic: addition, subtraction, multiplication, and division, and extracting one square root. You could say that this approach is more recipe than function, algorithm, or asymptotic analysis. Regardless, what makes this method novel is that it parses and gives the number of primes without the need to identify any specific primes other than the first 3, 2, 3, and 5i. There's no requirement for primality testing per se. For an in-depth exploration of this methodology, click here. Prime number counting methodology, twin primes. The world of twin primes is truly magical. For a detailed discussion of the factorization algorithms and symmetry groups, permutating matrices, orthogonal Latin squares, palindromes, equilateral triangles, complex polygons, etc., that ultimately determine the distribution of twin primes along 3 modulo 30 channels, go to this page. Twin primes demystified. Distribution algorithms and symmetries. There, you will be introduced to the beautiful palindromagon, pictured below, a complex polygon generated by tiered digital root dyad cycles central to the twin prime distribution channels, as well as modulo 90 factorization sequences. Its name comes from the fact that the triangulations generating it sum to a period 18 palindrome consisting of the 6 possible permutations of 3,609 sounds, which in turn can be permutated to produce 2 3 Latin squares with rows, columns, and principal diagonals, all summing to 18. Palindromagon distribution of perfect squares. All perfect squares within our domain, numbers not divisible by 2, 3, or 5, possess a digital root of 1, 4, or 7, and are congruent to either 1s or 1919s modulo 30. By definition, this includes the squares of all prime numbers greater than 5. We can easily explain this from a digital root perspective, given that the digital roots of members of our domain are restricted to 1, 2, 4, 5, 7, or 8. Numbers with digital root 3, 6, or 9 can't be members because they are divisible by 3. Thus, the digital root of squares is likewise restricted as follows, and note the palindrome. 1 and 1 equals 1, 2 plus 2 equals 4, 4 plus 4 equals 7, 5 equals 5 equals 7, 7 plus 7 equals 4, 8 equals 8 equals 1. By arithmetic law, perfect squares can only have terminating digits of 1, 4, 5, 6, 9, or 0. Only 2 of these final digits, 1 and 9, apply to our domain, i.e., for numbers congruent to 1, 11, 19, or 29 modulo 30. In turn, numbers congruent to 11, 29 are sequence digital roots 2, 5, or 8, and therefore, as we demonstrated above, there can be no perfect squares among them. And so it is that the distribution of squares is narrowed to numbers congruent to 1/18 modulo 30, which is to say they distribute along 2, and only 2, radii of the prime spiral sieve. 12 degrees, numbers congruent to 1 modulo 30, and 228 digs, numbers congruent to 19 modulo 30. This is also consistent with the fact that the quadratic residues for modulo 30, making them congruent with perfect squares, are 1 and 19. And it follows that all squares in this series distribute evenly to 2 of the 3 twin prime distribution channels, described above, negating a significant percentage of potential twin prime pairs. The matrix below illustrates the distribution of squares from 1 to 59, squares highlighted in blue. Distribution of squared members of domain. Summarizing the above relationships in mathematical terms, and in the knowledge that these modular relationships apply to the squares of all prime numbers, us 7, we get, for all n where n mod 30 equals 1, n2 mod 30 equals 1, for all nn where n mod 30 equals 29. N2 mod 30 equals 1 for all n where n mod 30 equals 11. N2 mod 30 equals 1 for all n where n mod 30 equals 19. N2 mod 30 equals 1. When the digital root of perfect squares is sequenced within a modulo 30x3 equals modulo 90 horizon, beautiful symmetries in the form of period 24 palindromes are revealed, which the author has documented on the online Encyclopedia of Integer Sequences as digital root of squares of numbers not divisible by 2, 3, or 5, A24092, 1, 4, 4, 7, 1, 1, 7, 4, 7, 1, 7, 4, 4, 7, 1, 7, 4, 7, 1, 1, 7, 4, 4, 1. In the matrix pictured below, we list the first 24 elements of our domain, take their squares, calculate the modulo 90 congruence and digital roots of each square, and display the digital root factorization dyad for each square, and map their collective bilateral 9-sum symmetry. Perfect squares, repeating digital root palindrome. Here's one more modulo 90 spin on perfect squares. Parsing the squares by their mod 90 congruence reveals that there are 96 perfect squares generated with each 4,360 equals 40, 432. Much more on the significance of number 432 elsewhere on this site. Here's the graphic. 96 perfect squares per 490 equals 360-degree cycle. Before leaving the subject of perfect squares, there's another hidden dimension of our domain worth noting involving multiples of 360, i.e., when framed as n more 1, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 49, 53, 59, 61, 67, 71, 73, 77, 79, 83, 89 var, modulo 90 and taking bipolar differentials of perfect squares as follows: 892, 12, x 306, 22, 832, 72, 8360 and 19, 792, 1 and 12, 8360, 17, 772, 132, 8360, 16, 732, 172, 360, 14, 712, 192, 360, 13, 672, 232, 360, 11, 612, 292, 360, 8, 592, 312, 360, 7, 532, 372, a 360x 4, 492, 412, a 360x2, 472, 432, a 360x 1 from alpha to omega. Not every beautiful theory has a physical application, but all fundamental physical theories found so far without exception have a type of beauty or symmetry. Michio Kaku, the God equation. The Ulam spiral arrays prime numbers in fragmented spiral and diagonal formations. Quoting from Wikipedia, Since in the Ulam spiral adjacent diagonals are alternatively odd and even numbers, it is no surprise that all prime numbers lie in alternate diagonals. What is startling is the tendency of prime numbers to lie on some diagonals more than others. From this one might deduce that the Ulam spiral is very likely a scrambled version of the Prime Spiral Sieve, as the latter demonstrates how all prime numbers, except 2, 3, and 5, are fundamentally arrayed along 8, and only 8 diagonals. It would appear, circumstantially, that the Prime Spiral Sieve is mathematically harmonious and perhaps isomorphic with the most complex and visually arresting Lie group, named E8, which, like the Prime Spiral Sieve, is 8-dimensional. E8 is pictured below, superimposed with a star polygon and the 8 radii of the modulo 30 factorization wheel. This group was recently in the news as possibly being a key to unifying theories in gravity and particle physics to create the proverbial theory of everything. The number 30 integral to the Prime Spiral Sieve is the Coxeter group number H, dual Coxeter number, and the highest degree of fundamental invariance of E8. You'll note, looking at the graphical representation of E8 below, that the perimeters of every one of its multiple concentric circles possesses 30 points. And, not surprisingly, E8 has 2, 3, and 5 torsion, and its exponents are the coprimes up to 30, i.e. 1, 7, 11, 13, 17, 19, 23, and 29 numbers you're very familiar with if you've read to this point, which brings us full circle. Graphic superimposes E8, star polygon, and mod 30 factorization wheel radii, the number 30 in Lie group E8. This graphic superimposes images of the star polygon, modulo 30 wheel factorization radii, and E8 graph of the Gosset 421 polytope as a two-dimensional skew orthogonal projection inside Petrie polygon, an emulation of the hand-drawn original by Peter McMullen, licensed by Creative Commons. License terms here. For 3D version of this graphic, step back 3 feet from the screen. We'll close with the graphic showing E24 superimposed with the 24 radials of a modulo 90 factorization wheel and the 15 points of a 15-point star represented with red dots, each point separated by 24 degrees, and we see that all 9 twin prime distribution channels are hit dead center. E24 modulo 9 factorization wheel radii. Your feedback welcome. Email gwc@hemibozo.com, Creative Commons license. This work is licensed by its author Gary William Croft under a Creative Commons Attribution Share, alike 3.0, unported license. Sitemap. Prime numbers demystified by 8-dimensional algorithms about the author. Finding Siamese primes using modulo 30 based algorithm. Finding Sophie Germain primes using modulo 30 based algorithm. Magic mirror matrix exposes perfect symmetry related to first 1000 prime numbers. Number 30, power integer. Comprehensive review, prime numbers. 8 chord factorization. Matrix, prime number root, angle. Factorization, Prime Spiral Sieve. Factorization and sieving algorithms. Prime number counting methodology. Twin prime distribution. Demystified proof by construction for the digital root. Sequencing of twin primes. Cumulative sum and indexing formulae. The mystery of the first 1000 prime numbers. Prime numbers, divisible only by 1 in themselves, are the building blocks of the mathematical universe. Their distribution appears random, yet they hold a captivating allure for mathematicians. Understanding their patterns unlocks deeper insights into the fabric of numbers. The Prime Spiral Sieve, a visualization tool, offers a unique perspective on this enigma. The Prime Spiral Sieve, also known as Ulam's spiral, is a graphical depiction of prime numbers. Invented by mathematician Stanislaw Ulam, it reveals unexpected patterns in the seemingly random distribution of primes. By arranging numbers in a spiral, the sieve exposes hidden relationships and clusters of primes. Constructing the Prime Spiral Sieve is a simple yet elegant process. This method, often referred to as Ulam's spiral, is a fascinating way to visualize prime numbers and their distribution. It begins with a straightforward setup, but reveals complex and intriguing patterns that have captivated mathematicians for decades. Begin by arranging natural numbers in a spiral pattern, starting with 1 at the center. This spiral can be drawn on graph paper or generated using computer software. As you continue to add numbers in a counterclockwise direction, the spiral grows outward, creating a unique and visually appealing structure. As you move outward, mark the prime numbers while leaving non-primes unmarked. Prime numbers are those greater than 1 that have no divisors other than 1 and themselves. By highlighting these primes, you begin to see a pattern emerge. The primes stand out against the backdrop of non-primes, creating a striking visual effect. The resulting pattern reveals diagonal, horizontal, and vertical lines that are surprisingly rich in primes. These lines are not random. They suggest a hidden order within the seemingly chaotic distribution of prime numbers. Mathematicians have long been intrigued by these patterns, as they hint at deeper mathematical truths. These alignments, known as Ulam's diagonals, suggest an underlying order to prime distribution. Named after the mathematician Stanislaw Ulam, who first discovered this phenomenon in 1963, these diagonals have been the subject of much study and speculation. They raise questions about the nature of primes and whether there is a more profound structure governing their placement. Stanislaw Ulam's discovery was serendipitous, made during a meeting when he began doodling numbers in a spiral. To his surprise, the primes formed distinct diagonal lines. This accidental discovery has since become a valuable tool in number theory, providing insights into the distribution of primes and inspiring further research. The Prime Spiral Sieve is just one of many methods used to study prime numbers. Other sieves, such as the Sieve of Eratosthenes, also play a crucial role in identifying primes. Each method offers unique insights and contributes to our understanding of these fundamental building blocks of mathematics. Prime numbers are more than just a mathematical curiosity. They are essential to various fields, including cryptography, computer science, and even quantum physics. The patterns revealed by the Prime Spiral Sieve and other methods help us unlock the secrets of primes, leading to advancements in technology and science. Interestingly, prime numbers also appear in nature. The arrangement of seeds in a sunflower, the branching of trees, and the spirals of shells all exhibit patterns that can be related to primes. This connection between mathematics and nature underscores the universality and beauty of prime numbers. As we continue to explore the mysteries of prime numbers, new discoveries await. The Prime Spiral Sieve is a testament to the elegance and complexity of mathematics, reminding us that even simple processes can lead to profound insights. The journey of understanding primes is ongoing, and each step brings us closer to unraveling the secrets of the universe. The Prime Spiral Sieve provides a powerful visual representation of prime distribution. The clustering of primes along certain diagonals suggests that prime numbers are not randomly scattered. Instead, they exhibit a degree of predictability, hinting at deeper mathematical relationships. The sieve allows us to observe these patterns and formulate conjectures about their nature. Beyond their theoretical significance, prime numbers have practical applications in various fields. These unique numbers, which are only divisible by 1 and themselves, have fascinated mathematicians for centuries. But their importance extends far beyond pure mathematics. Cryptography, for instance, relies heavily on the difficulty of factoring large numbers into their prime factors. This is because prime numbers form the backbone of many encryption methods. When you send a secure message or make an online purchase, prime numbers are at work behind the scenes, ensuring your data remains private. This property ensures the security of online transactions and data encryption. Without prime numbers, the secure transfer of information over the internet would be nearly impossible. They help create complex keys that are difficult for hackers to break, thus protecting sensitive information from unauthorized access. Understanding prime distribution can lead to the development of more efficient algorithms and stronger cryptographic systems. Researchers are constantly exploring new ways to utilize prime numbers to enhance security measures. By studying the patterns and properties of primes, they aim to create more robust encryption techniques that can withstand even the most sophisticated cyber attacks. Beyond cryptography, Prime numbers also play a crucial role in other technological advancements. For example, they are used in error detection and correction algorithms, which are essential for reliable data transmission in satellite communications and GPS systems. In space exploration, primes help ensure the accuracy of data sent back to Earth from distant spacecraft. In the financial sector, prime numbers are used in various algorithms to analyze market trends and predict economic behaviors. They help in creating models that can forecast stock prices and assess risks, providing valuable insights for investors and analysts. In the field of medicine, prime numbers contribute to advancements in medical imaging technologies. Techniques such as MRI and CT scans rely on complex mathematical algorithms, some of which are based on prime number theory to produce clear and accurate images of the human body. The influence of prime numbers even extends to the arts. In music, they are used to create unique rhythms and harmonies. In visual arts, prime number patterns can be found in various forms of design and architecture, adding an element of mathematical beauty to creative works. Educators also recognize the importance of prime numbers in teaching mathematical concepts. By introducing students to the fascinating world of primes, they can inspire a deeper appreciation for mathematics and its real-world applications. As we continue to explore the potential of prime numbers, their applications will undoubtedly expand, driving innovation across various fields. From securing our digital world to advancing scientific research, prime numbers are an integral part of our technological landscape, shaping the future in ways we are only beginning to understand. The Prime Spiral Sieve exemplifies the inherent beauty and elegance of mathematics. A seemingly simple arrangement of numbers reveals intricate patterns and unexpected connections. This visual representation of prime distribution sparks curiosity and invites further exploration of the mysteries hidden within the world of numbers. Stanislaw Ulam's accidental discovery of the prime spiral during a boring meeting highlights the serendipitous nature of mathematical breakthroughs. His simple yet profound visualization tool continues to inspire mathematicians and enthusiasts alike. The sieve serves as a reminder that even in seemingly random distributions, underlying patterns and order may exist, waiting to be uncovered. Prime numbers, with their elusive nature, have fascinated mathematicians for centuries. These numbers, which are only divisible by one end themselves, hold a special place in the world of mathematics. Their fundamental importance cannot be overstated, as they are the building blocks of number theory. From ancient Greek mathematicians like Euclid, who proved that there are infinitely many primes, to modern-day researchers, prime numbers continue to captivate and challenge. One of the most intriguing visual representations of prime numbers is the Prime Spiral Sieve. This method provides a captivating glimpse into their distribution, revealing hidden patterns that are not immediately obvious. These patterns spark further inquiry and lead to deeper questions about the nature of primes. Why do they appear where they do? What governs their distribution? These questions drive mathematicians to explore and discover new insights. As we delve deeper into the world of numbers, we find that prime numbers are not just isolated entities. They are connected to various branches of mathematics, including cryptography, where they play a crucial role in securing digital communications. The Prime Spiral Sieve serves as a reminder of the beauty and complexity inherent in mathematics. It shows us that even in the seemingly chaotic world of numbers, there is order and structure waiting to be discovered. The enduring allure of prime numbers lies in their mystery and the endless possibilities they offer for exploration. As we continue to study them, we uncover more about the fundamental nature of mathematics and the universe itself. The journey of understanding prime numbers is a testament to human curiosity and the quest for knowledge, a journey that is far from over. Pause 3s. As we continue our journey through the enigmatic world of prime numbers, we find ourselves standing at the intersection of mathematics and spirituality. One intriguing perspective that merges these two realms is the study of Quranic numerology. This approach explores the divine numerical patterns within the Quran, offering a unique lens to view the sacred text. The title, The Divine Numerical Symphony, a theory of everything in Quranic numerology, is chosen for several reasons. Divine Numerical Symphony. The word divine reflects the belief that the patterns within the Quran are part of its divine origin. It suggests that the numerology is not merely human-made or coincidental, but a reflection of divine wisdom and intentionality. Numerical highlights the focus of the study on the numbers and numerical patterns found within the Quran. Symphony implies harmony, coherence, and beauty in the arrangement of these numbers. Just as a symphony has multiple instruments playing together to create a harmonious piece, the numerical patterns in the Quran are seen as working in unison to convey deeper meanings and messages. A theory of everything. This phrase, borrowed from physics, where a theory of everything aims to unify all fundamental forces and particles, is adapted here to suggest that the numerology in the Quran provides a comprehensive understanding or unification of its structure, themes, and messages. It implies that this numerological study offers a holistic view of how numbers integrate into the Quran's divine message, uniting various aspects of its composition. Quranic numerology. This specifically narrows the scope to numerology as it pertains to the Quran. It signals to the reader that the study deals with the exploration of numbers within one of the world's major religious texts, emphasizing an Islamic theological perspective. This title encapsulates the aim to explore the Quran not just as a text of religious guidance, but as a canvas of numerical patterns that reflect divine order and perfection. Present an overarching theory that ties together various numerical elements into a coherent narrative, suggesting a deliberate divine design. Invite readers into a contemplation of the Quran that blends spirituality with intellectual curiosity about mathematics, fostering a deeper appreciation of the text's multifaceted nature. Thus, the title is meant to be both descriptive and evocative, suggesting a journey into the mysterious and beautiful interplay between faith, numbers, and divine revelation. The study of Quranic numerology opens up a realm where mathematics and spirituality converge, offering a profound appreciation of the divine numerical symphony. Pause 3s. And so, as we reflect on the prime spirals and the divine patterns, we are reminded that the beauty of numbers transcends the boundaries of disciplines, touching the very essence of our quest for knowledge and understanding. The journey continues, ever enriching our minds and spirits.